Totally agree.
So far we've got to cosmic chirality,
But that first statement, having conjectured that molecular chirality is the product of universal chiral force in nature, Pasteur never said that. You didn't put quotes around that. He didn't say that. I know what Pasteur said. You know, but
I'll check it
I've
out.
studied. He never said
all right,
that.
I'll check it out.
Did you? In fact, you know the volume of topics in stereochemistry?
Yeah.
The volume 24 I did with Bert Meyer
Oh,
and
yes.
Rulin. No,
I haven't got that.
the preface. I wrote the preface.
All right,
of
I'll look
thing.
at that. Yeah.
And in there is
Okay,
the
great.
truth.
Okay. Right. So far we've reached cosmic chirality. But in fact, to be more precise, it's cosmic true chirality. Now we're going to move on to cosmic false chirality, which brings us to CP violation. As you'll see, parity violation is the quintessential truly chiral force in the fabric of the universe. I hope to convince you that CP violation is the quintessential falsely chiral force.
Remind me what CP stands for again.
Charge, conjugation, and parity. So, as well as applying space inversion, parity, you apply charge conjugation, that's particle-antiparticle exchange. So you go from the real world to the anti-world. Right, CP violation. It first turned up in 1964. This was the observation. There's this object called this particle, the long-lived neutral K meson. It has two distinct decay channels, producing these two distinct sets of products. That's a negative pion, a right spin polarized positron, left spin polarized neutrino, or you can get a positive pion, a left spin polarized electron, a right spin polarized antineutrino. And it was found in 1964 that there was a decay rate asymmetry. The decay rate of those two distinct sets of products was slightly different, but real and measurable and easily reproducible. And because those two sets of decay products are interconverted by CP, negative pion, positive, that's which is the anti, which is what, but they're right spin polarized electron, left spin positron, left spin polarized electron, left spin polarized neutrino, right spin polarized antineutrino. Those are interconverted by CP. They're CP enantiomers, if you like. The fact that there was a decay rate asymmetry measured, that showed that CP is actually being violated in this decay. Now this automatically implies time reversal violation from the CPT theorem. The CPT theorem says the Hamiltonian is invariant to CPT, all three operations, even if it's not invariant to one or more of those operations. So even if if CP is violated, there has to be a balancing violation of T to make CP invariant overall. That's the cornerstone of particle physics. Now, in fact, so that was what was observed, and so T violation was implied from CP violation. But in the 90s, T violation was actually observed directly in the form of slightly different rates of particle to antiparticle, and going back the way, antiparticle to particle, those two rates were found to be slightly different, and that was a direct observation of T violation. And that shows you, it corresponds to a breakdown in microscopic reversibility. The rates for the two different directions are slightly different. That's breakdown of microscopic reversibility. But a central feature here, which I can't emphasize too much, is a particle and its antiparticle. They've got the same rest mass if CPT is conserved. So that means these particles and antiparticles in these processes, they've got identical masses and intrinsic energies. So you see, that shows you CP violation affects the kinetics but not the thermodynamics of these particle-antiparticle processes. Right.
Just a bit slower, maybe.
A bit slower.
Just to come back again.
Right.
So I understand T violation implies breakdown of microscopic reversibility. And then what did you say after that?
A particle and its antiparticle have the same rest mass if CPT is conserved. That's a key consequence of the CPT theorem. From that you can show, provided CPT is conserved, a particle and its antiparticle have identical rest masses. That's a central plank of elementary particle theory.
Yeah.
So
right.
That means that these particles and antiparticles, they've got identical masses, but the rates to go from one to the other and are different. That means CP violation is affecting the kinetics, but not the thermodynamics.
And the latter you may have expected, but you didn't know for sure. So now you know it. You mean?
Yeah. But,
so it wasn't. It could not. I mean, could that not be measured directly? That that a positron and electron have the same mass, rest mass. This cannot be measured directly.
Yeah, but to what degree of accuracy?
Yeah, okay.
People have been busting themselves for years to find tiny differences between mass of a proton and an antiproton, but they've not done so. But interestingly, atomic and molecular physics will provide experiments 10 orders of magnitude more sensitive. This is why people are so keen to generate significant amounts of anti-hydrogen at places like CERN, enough to do spectroscopy on. Because if you can measure a few of the transitions, atomic transitions spectroscopically, hydrogen and anti-hydrogen, and look for tiny differences, that's something like 10 orders of magnitude more sensitive than looking for a mass difference between a proton and an antiproton.
How do you store such stuff?
How
does one store anti-hydrogen?
Great difficulty. Magnetic bottles, magnetic containers. Did you not read, what was it? The guy who wrote the Da Vinci Code, he had one about someone stole a bottle of anti-hydrogen or something from CERN and used it to blow up the Vatican. Switched off the magnetic field and bang.
Good.
Right. Right, now, back to chemistry. Absolute enantiomer selection. So consider then a unimolecular process in which an achiral molecule R generates a chiral molecule M, or its enantiomer, chiral enantiomer N star. I'll give you a realization of this later. This electrocyclic reaction, that can be R, that can be M, that can be N star, for example. That gives you a concrete realization. Now, in the absence of any sort of chiral influence, M and N star have got the same energy. So here we are, this is a potential barrier diagram. There's our barrier taking you to N star. Absence of a chiral influence, M and N star have got the same energy. So if you allow this reaction to reach thermodynamic equilibrium, you can never get an excess of one over the other. You have to equal us. Now, a truly chiral influence lifts the degeneracy of M and N star. Parity violation, circularly polarized light, magnetochiral influence. So now, if you let the reaction go to equilibrium, you'll get an excess of M over N star. There'll also be kinetic effects, because the barrier's heights will be, transition states will be affected. They'll be chiral and they'll be affected as well. But fundamentally, it affects the thermodynamics. Now, a falsely chiral influence, as I tried to explain, it doesn't lift the degeneracy of M and N star. So that means, in a falsely chiral influence, like parallel electric and magnetic fields, you can never generate an enantiomeric excess if you let the reaction go to equilibrium.
Unless you have J dot B.
Yeah, that's worth thinking about, isn't it? J dot B, yes. Well, but that's truly chiral.
Yes.
Yeah.
That would work, even in equilibrium.
Yes, so try and think of how you would set up a J dot B apparatus in the laboratory there. That could be good, yeah. Microscopic reversibility now. This follows from the behaviour of the quantum mechanical transition amplitude under time reversal. So we just imagine abstractly a transition from some initial linear momentum state P of one or more interacting particles to some final state P prime. Under time reversal, that transition amplitude will now look like this, minus P prime to minus P, is sort of reversing the process. And those two transition amplitudes are equal. And if you build this into a quantum statistical average over all colliding particles at equilibrium, you get to the principle of detailed balancing. And out of that, you can sort of generate these pictures that we use in chemistry of is the potential barrier. And from that, via detailed balancing, it implies it's the same potential energy barrier, whichever way you go, from R to N or N to R, they're going backwards and forwards over the same potential barrier. And that's what microscopic reversibility means in chemistry. That's how one imagines it. Let's now let's apply a falsely chiral influence like collinear electric and magnetic fields. Now, time reversal is no longer a symmetry operation because it generates the enantiomorphous influence. So here we go. There's that transition amplitude describing the process in simple terms. And we've applied externally parallel electric and magnetic fields. Under time reversal, we've got the reverse process, but look, we've reversed the magnetic field relative to the electric. So what you can say is that transition amplitude in parallel fields equals that amplitude in anti-parallel fields. But you can't say that that amplitude in parallel fields equals that in parallel fields. But now if you apply parity, you now reverse both. You reverse the electric field as well as the magnetic, so you're back to parallel fields. But if the particles are chiral, you now allow the particles to be chiral. And so these are now the mirror image enantiomers of those particles. So the transition amplitude from P to P prime equals that for the reverse process involving the enantiomeric particles in the presence of a falsely chiral influence. So you now go to this deeper principle of enantiomeric microscopic reversibility. So now you're balancing the initial process with the reverse process involving the enantiomeric particles. And so that's a deeper principle of enantiomeric microscopic reversibility. And let me say, this isn't completely crazy off the top of my head. I got the idea from this out of Landau and Lipschitz physical kinetics. They tried to generalize their discussion of detailed balancing. And they suggested this. But they weren't considering the external influence. They weren't considering, they didn't allow for this falsely chiral influence. So what we have then, for reactive molecules in a falsely chiral influence, we only have enantiomeric microscopic reversibility, and it's based on this. That process from R to M, the rate that the transition amplitude is the same as that from M star back to R. So that's enantiomeric microscopic reversibility. You apply time parity as well as time reversal. So what that means is it's the same potential energy barriers for the forward and reverse enantiomeric processes, but say R to M and M back to R, you see, it's a different barrier. So that barrier is the same as that, forward and reverse, and that barrier in that direction is the same as that one there. So that is how you can visualize enantiomeric microscopic reversibility. Now, if the molecules are achiral, M and N star are the same, and those two barriers coalesce, so there's nothing new there. But if they're chiral, they don't. Now, here's a physical realization, or a paper anyway. So this is an electrocyclic conrotatory ring closure of a butadiene. This is Woodward-Hoffman territory. famous Woodward-Hoffman rules were applied to this. So you have this butadiene, AB groups there. So that's R. You can go this way with, you see, you can get the conrotatory process going that way, generating that enantiomer, or the conrotatory process can go the other way, generating that. Those two are mirror image enantiomers. So now apply parallel electric and magnetic fields. As far as the electric field is concerned, that serves to align the molecules. They'll be dipolar, you see. There's a C2 symmetry axis all through there, which implies an electric dipole in that direction. So they'll align with that electric dipole parallel to the electric field. So you can now forget the electric field. It's done its stuff and just align the molecules. Or if the molecules are starting off aligned, as on the surface, you don't need the electric field. Okay, there's the magnetic field. Now you've got this rotational motion here, and that will generate rotational magnetic moment because there's partial charges on these groups, around the molecule. So you have a rotational magnetic moment, and there'll be a net component in this direction pointing down for that sense of rotation. So in the presence of the magnetic field, that's anti-parallel to the field. So that will tend to raise the barrier for going that way. Whereas going that way, in the opposite sense, to produce the other enantiomer, the net magnetic moment's pointing that way, parallel to the field, so that will lower the barrier. So now that's giving you a picture of how the barrier goes up in that direction and down in that direction. But then coming back the way, see, the magnetic field's now pointing upwards, coming back from there to there, so that barrier is lower. But coming back from there to there, it's pointing down, so the barrier is higher. So there you are, there's a simple molecular realization of this strange idea of enantiomer. So that barrier from R to N is the same as from N star to R. There you are, that's enantiomeric microscopic reversibility. Now, here we can bring up an analogy with CP violation in the K-meson system. Okay, so we've got molecule R going to M one way or N star the other. M and N star are p enantiomers of each other. And in the presence of a falsely chiral influence, Kf and Kf star are different. And Kb and Kb star are different. Now that's it. In the presence of, collinear A, E, and B, or whatever, falsely chiral influence. Now that's exactly analogous to that first manifestation of CP violation. Long-lived neutral K-meson can give you these two sets of decay products, and those are CP enantiomers of each other. And it's actually observed that Kf and Kf star are different. That's actually observed. It's real observation of microscopic reversibility. So we have a very nice analogy here. You see here, it's P enantiomers involved. Here we have CP enantiomers involved. So we can conceptualize this decay rate asymmetry of the long-lived K-meson from a breakdown in microscopic reversibility due to a time non-invariant CP enantiomer influence in the forces of nature. See, it's time non-invariant CP enantiomorphism, because the CPT theorem guarantees that the two possible distinct CP enantiomorphous influences are interconverted by T. See, so CP is violated, T is violated, but CPT holds overall. It's analogous here. P is broken, T is broken, but PT holds overall. So there is a direct and beautiful analogy there. Now, those of you who've been following and know something about thermodynamics versus kinetics will realise there's a pathological problem here. That seems to be because if R to M is favoured over R to M star because of these this breakdown of microscopic reversibility, if you let the reaction keep going, then M, you'll get an excess of M building up over an excess of M star. So it means that thermodynamic equilibrium, you'll have a big excess of one over the other, which isn't allowed because the energies of M and N star are the same in the presence of the falsely chiral influence. That's the essence of it. Yeah. Well, this conflict between kinetic and thermodynamic requirements can be resolved by including other racemization pathways. So you allow for other possible intermediates by which M and N star can interconvert. And there's an infinite number of them. There's all the excited quantum states of R possible, and you can imagine other species as well as intermediates. Then at true thermodynamic equilibrium, that means when all possible racemization pathways have equilibrated, you find that the concentrations of M and N star are the same. And the reason is, the different enantiomeric excesses associated with the different pathways cancel. So the excess generated going through R, for instance, might favour M, but going through R double prime, it might favour M star. And when you add them all up and allow them to equilibrate, which is what true thermodynamic equilibrium means, you get equal amounts. And the proof, that can actually be proved from the unitarity of the scattering matrix. The probabilities of all possible transitions to and from a given state must sum to unity. And in fact, it's unitarity, not microscopic reversibility, that lies behind the validity of Boltzmann's H theorem, and hence the second law. And that was actually shown after CP violation was discovered. People were terribly worried because, from a similar argument, it implied that because we've lost microscopic reversibility, we've lost Boltzmann's H theorem, and hence the second law. People were very worried. But then people like Edward Teller worked on this in the late 60s and showed via unitarity you can recover Boltzmann's H theorem without even if microscopic reversibility breaks down, as it does in the CP violating systems, you can still recover Boltzmann's H theorem and hence the second law via unitarity. So that saves us in the chemical case as well. And I can give you actually that molecular example. Reveals a possible example of another intermediate. You see, look, if you say have A here and B here, and A here and B here, let's say the A's are much bulkier than the B's, so it's not as favourable. But if you reverse A and B, then what will happen is you'll find it goes the other way, sort of thing. I need you to look at that more closely, but it does work. That's a possible alternative racemization pathway that favours the other enantiomer over the first one. So finally then, CP violation, false chirality and catalysis. Okay, so as I've been emphasising, the force responsible for CP violation lacks a CP and T invariance, but it's CPT invariant overall. So that's analogous to the falsely chiral influence, like collinear E and B, which is characterised by lack of P and T invariance separately, but PT invariance overall. So you've just added a C in here. So it's CPT instead of PT. It's deeper. So the force responsible for CP violation, then, it's the quintessential falsely chiral influence in particle physics and in the universe, actually. It's time non-invariant enantiomorphism in the fabric of the universe. So a falsely chiral influence, curiously, it acts as a genuine chiral catalyst. Although it's falsely chiral, it's a chiral catalyst using the true sense of the word of a catalyst, because a catalyst affects rates but not thermodynamics in chemical reactions, you see. So falsely chiral influence, it modifies potential energy barriers to change relative rates of formation of enantiomeric products, but without affecting their relative energies and hence the equilibrium of thermodynamics. So there's a curious clash of nomenclature here. A falsely chiral influence acts as a genuine chiral catalyst. What people talk about as chiral catalysts, they're not perfect catalysts in the sense that they will also lift the they'll affect the thermodynamics as well because they're chiral objects, truly chiral. Right. So anyway, I've mentioned before from the CPT theorem, rest mass of a particle and its antiparticle are identical, even if CP is violated. So CP violation is therefore analogous to chemical catalysis, since it affects the rates of particle-antiparticle processes via a breakdown in microscopic reversibility without affecting the thermodynamics. So we mere chemists can actually conceptualize CP violation better perhaps than physicists, because we know about catalysis, you see. People get very worried about CP violation and what does it mean, violation of time reversibility. Well, really, it's a breakdown of microscopic reversibility, and it's just affecting the kinetics rather than thermodynamics, and so it's analogous to chemical catalysis.
We should discuss this with Donna Blackmore. Sorry?
What's the she?
No, because she doesn't make the difference between thermodynamics.
Did she? Okay. So there we are, summary. Lord Kelvin's and Louis Pasteur's legacy. So we live in a chiral world from the very fabric of the universe to the nuts and bolts of life. Everything in the universe is intertwined and basically inseparable. So if you want some further reading, there's the new edition of my book, which has got some of this symmetry stuff in it, but it's got practical things like, theory of optical rotation, circular dichroism, Faraday effect, Raman optical activity, blah, blah, blah. And magnetochiral phenomena in the edition. But also there's this lovely book from Georges Vanier, came out about a year ago. Similar sort of, it uses symmetry, real proper physics symmetry arguments like I do, but in a broader context now. So the two books are highly complementary. So if you buy one, it doesn't mean you don't have to buy the other.
Thank you. Thank you very much for your two very interesting lectures on the foundations of symmetry, breaking, chirality, and time reversibility, and so forth. What remains to be discussed?
Just a little question. What's this system? It's experimental. This reaction there, yes. It's experimental or only theoretical? Yeah.
No, that's a well-known reaction, although nobody's ever applied electric and magnetic fields.
Okay, this has not been measured.
No, it's just a suggestion of a realization of.
Yeah. So I was wondering, what is the intensity of the anatomic cases that can be obtained?
Well, that would be of tremendous fundamental importance if anyone were actually to show reproducibly that you could generate an excess of M over N star with parallel and then the other with that. Real fundamental stuff. Yeah.
Your friend in Toulouse, he tried to take it? Your friend in Toulouse?
He's been trying to do something similar, not this reaction. Not quite sure. I can't remember what he had in mind, but it's still very much on his list of whether he ever gets round to it.
But as far as external factors is concerned, the mechanism with an unpolarized light and a magnetic field is potentially one which may be strong. And there you actually know already how strong the effect is.
Well, we do. Yeah, we do.
So that's really all we know, I guess.
But there's no problem there. That we know that had to work because one can see from just the simple symmetry arguments it's true chirality.
Yes.
No question, it has to work. Whether it's detectable or not, well, we now know it's detectable, which is great. But the other one,
yes,
falsely chiral influence, I think it will work by analogy with the elementary particle case. That seems to be a good analogy. But there may be something missing, and it may be nonsense.
I mean, to address Mark's question, and Mark is not here, one would really like to know how important this is, in fact, relative to thermal fluctuations for given concentrations. Because it may well be that we are in situations in prebiotics that we have either low enough concentrations so that the fluctuations are high enough, in which case such mechanisms can easily be ruled out. Or it may be that this is not the case, that the concentrations are generally very high, so the fluctuations are very small. Chemical reactions are rapid, in which case those effects are perhaps crucial.
Yes.
Or more, they would be determining what's happening rather than chance.
Yes.
Because the effect of chance is too small if the concentrations are too high. So that's a qualitative question that one needs to work on if one either wants to pursue this line of research or wants to shoot it down, as Mark perhaps wants to do.
But it could provide an answer to why chirality, well, something deeper. That's to not simply just a question of nuts and bolts of the right hand, but the matching handedness. Why there's more to it than that, and I think there is more to it than just the handedness of. You have to get the handedness of your nuts and bolts right. I think there's more to homochirality than that. There's some fundamental physics there.
Why do you say this again? I maybe missed it. Why do you say this?
Oh, why do I say this? It's more than just matching nuts and bolts. Which is what Mark is saying. You need homochirality. Now, Mayer says you don't need chirality at all. You could have
No, I didn't say that. I think that maybe primitive artificial life which can be built up on silly.
Sorry.
But the life that we know it, of course, is homochiral, and we can understand that.
Right.
But we cannot exclude the possibility of having artificial life of some kind, which is based on acidic.
Artificial life or prebiotic replicating systems, which are actually not living, but were precursors, were a stepping stone towards proper life.
You see, the alpha helices and the beta sheets are chiral, and they cannot be formed with racemic species.
Yeah.
And therefore, if we take the alpha helices and the beta sheet, then it's very important in pathologies in the very early stages of evolution that we must have chirality. But if you consider some kind of artificial life which is not evolved very far, I think this can be also built up on racemic species.
But I'm asking, maybe that isn't life. That's a precursor, but it isn't.
Yeah, then you're alluding to another question: what is life? We can discuss this probably sometime again.
I mean, does Gunther know of any replicating molecules that are achiral?
Replicating?
I mean, there are some. We have the Terford replicator.
Well, it is Rebex system. I don't know what it was achiral. The Rebex system was
The
achiral.
Rebex system was chiral because it was based on Arrhenius.
There are two groups. I think it was a music compound. Because it had two groups.
I think one part was derived from Arrhenius, so additional.
Yeah.
So it's chiral. Achiral was the Terford replicator.
Which one?
The Terford replicator. There's this Arrhenius. This was achiral.
So in conclusion, replication one can have without chirality, but how about polymerization? Is there any replication that you know of with polymerization and no chirality.
I think that if you take the syntactic polymers, I think there are also the syntactic polymers which are composed from DL.
Yeah.
I think they also need some kind of recognition, some type of stereospecificity.
You like achiral PNA.
Yeah. Right. And people are not. Yes. At least Peter Nielsen is not, at least not doubting the possibility of PNA, achiral PNA being autocatalytic, although it's not detected, measured yet. And by the way, and that's the reason, I guess, achiral PNA can still form spiraling.
Yeah, of course. If you touch a chiral group, ligand on one end actually reduces the formation of the chiral helical structure, right?
Okay, so we have some 40 minutes break before we start with Peter's talk.
How much time do we have?
Now?
Yeah.
Now 40 minutes.
Oh, wonderful. Okay.
Good. So thanks, Lawrence, again.